JMO 2024 problem 3. Let A of n be the sequence defined by A of 1 equals 2 and A of n plus 1 is equal to A of n to the power of n plus 1 minus 1 for each integer n at least 1. Suppose that p is greater than 2 is prime and k is a positive integer. Prove that some term of the sequence A of n is divisible by p to the k. Okay. For this problem, I told you the most useful idea is what? Idea 1 concerning a small example. Again, we want to use this idea like problem 2 and also problems of USAJMO 2024 and also for 2023 and all the exams. This idea is so much powerful. But a small example on what? Let's use a small example on P. Okay? First P that we should check is what? P2? No, because it says P is greater than 2. So the first P is 3. And I want to see, it says k is a positive integer. So you should prove what? You should prove for each power of 3 there exists an element in our sequence that is multiple of that. Okay? So let's see what happens here. A1 is what? Is 2. A2 is what? You should raise A1 to the power of 2. Look, A2 is A1 squared minus 1, which is 3. A3 is what? Is 3 to the power of 3 minus 1, 27 minus 1, 26. A4 is what? 26 to the power of 4 minus 1. And we should continue and write these numbers. Now, I want to prove that let me tell you first, for example, when we have V2 of something, V2 of 24, you should prime factorize 24 and write 2 cubed times 3 and see power of 2 is what? Is 3. For example, V2 of 18 is what? If you prime factorize, it's 2 to the 1 times 3 squared. Power of 2, 1. So V2 of 16 is what? 16 is 2 to the 4 is 4. Okay, V2 of 5 is what? Is 0, because power of 2 is 0. V3 of 18 is what? Is 2, because 3 squared, and so on. Now we want to prove that V3 of, for example, AI is large, A something. If we consider V3 of an plus 1, if we use this equation, it will be what? V3 of an to the n plus 1 minus 1. When we see this, it is similar to a theorem. It is what? Lifting the exponent. Okay, or LTE. It says what? Because here we know our P is odd. If P is an odd prime, and P doesn't divide X, so it's idea 2. P doesn't divide Y. It was also useful in AIME. I will tell you at the end of this solution. The AIME problem was what? And you can do that one as homework. And I think I released full solution of that problem. So if you saw my previous videos, you could solve this problem if you combine this with a small example. So if we divide this, then we can say Vp of x to the n minus y to the n is equal to, for plus also we have formula. When p is 2, we have formula. We have 4 cases. Vp of n, okay? Now we want to use this. So here, if we want to use this, we know that 3. Let's see the conditions that should be satisfied to use this. 3 shouldn't divide an. 3 shouldn't divide 1. Here, 3 should divide an minus 1. And then we can apply this. So first, let's see what happens. These 3 conditions, we know this one is always correct. if an because of this should be 1 mod 3. Okay, and if an is 1 mod 3, 3 doesn't divide an. So we should find ans that are 1 mod 3 if it is possible. Let's check, can we use this or not? So let's move it here. We should consider these numbers mod 3. First one, okay. So a2 you should raise to the power of 2. Previous one. This one raised to the power of 3. Raised to the power of 4. Okay, so if you check a1 is 2, or instead of 2 you can write negative 1. Negative 1 squared minus 1 is 1 minus 1, 0. 0 squared minus 1 is minus 1. As you can see, 26 is minus 1. Again, minus 1 to the 4 minus 1 is 0. Minus 1, 0. So we cannot reach an that is equal to 1 mod 3. Okay, so here we don't have an that is 1, but like AIME problem, if it is even, you can consider an squared. Then an squared is negative 1. So as you can see, it is a1, it is a2, a3, a4, a5, and easily by induction we can prove a sub odd numbers are negative 1. So if we consider n odd, suppose n is odd, okay? So v3 of an plus 1, let's see is what? Is v3 of an to the n plus 1. Because n is odd, you can say n is, for example, 2k minus 1. Okay, so let's write v3 of 2k is equal to a 2k minus 1 to the power of 2k minus 1. And we know a 2k minus 1 is negative 1. So if we consider v3 of a 2k minus 1 squared to the k minus 1, then this part is 1. You can call this one, for example, as x and this one as y. So because x squared is x is 1 mod 3, so x minus 1 is multiple of 3, and this one is non-multiple of 3, this one is non-multiple of 3. And we can use what? We can use LT. So if we use LT, it would be what? Let's write. We can write it's equal to v3 of a2k minus 1 squared minus 1 plus v3 of what? K. Now, because we had k in the problem, let's use another variable. For example, r. Okay, so r, 2r minus 1 to the 2r, 2r minus 1 squared to the r, 2r minus 1 squared plus v3 of r. Okay. If r is multiple of, suppose, for example, r is equal to, it says for any power of 3, for example, any power of p, like k, prove that there exists an element. So if we define r as 3 to the k, so it will be what? It is at least k. V3 of this is at least k. And also we can say k plus 1 because it is also multiple of 3. So this one is multiple of 3 to the k because v3 of that is multiple of k plus 1. So we proved that v3 of a 2 times 3 to the k is at least k plus 1. So 3 to the k divides this. Also you can say v3 of a 2 times 3 to the k minus 1 is at least k. So for 3 we could prove this problem. Now let's check another number. Here we can see that we can try to generalize it, but let's check also P5 to see what can we say for P5. Again, if we consider our numbers, first number is 2. Okay, so for P5, if we consider first one is 2, next one is 2 squared minus 1, 3. Next one is 3 cubed minus 1, which is 26, like this. And if we consider these numbers mod 5, So we can write 2, 3, 26 is 1. It is A1, A2, A3. Next one is what? 1 to the power of 4 minus 1, 0. Next one is what? It's A4, A5. So 0 to the power of 5 minus 1, negative 1. A6 is what? Negative 1 to the 6 minus 1, 0. A7 is what? 0 to the power of 7 minus 1 minus 1. A8 is what? Negative 1 to the power of 8, 0. So obviously, because when we have negative 1, it is A odd, then next one is A even. Negative 1 to the power of even is 1 minus 1, 0. And again, we can say 0, negative 1. So from here, we have 1, 0, 1, negative 1. From here, A4, we have 0, negative 1, 0, negative 1, 0, negative 1, and so on. Now, I know that A, again, 2k are even numbers. A, 2k are 0. So we can say, if we want to calculate, again, we want to apply LTE, V5 of A2k is equal to what? V5 of A2k minus 1. And suppose A2k, k is at least 2. Or AK is at least 3. Okay, at least 6. The previous one is negative 1. A2k squared. No. To the 2k minus 1. And because we know A2k minus 1 is negative 1 from this one, so we can say V5 of A2k minus 1 squared. k minus 1. Now we know it is 1. Mod 5. So these conditions would be satisfied if you consider this one as x, this one as y. 5 divides this minus 1 because it is 1, because this one is negative 1, squared is 1. Now we can apply LTE. It will be V5 of A2k minus 1 squared minus 1 plus V5 of k. Again, because we have k, I should use another variable. Pay attention to this point, because maybe the person that want to check your answer think that this k is the k problem says, let's write s. It's better to not use same variables. So 2s minus 1, this s, 2s minus 1, 2, v5 of s. So if s is 5 to the k again, we can say what? It's at least v5 of that, at least k plus 1, or you can say 5k minus 1. Then it's at least k. Okay? And this number is multiple of 5 to the k. Let's check one more prime, 7, and then we will generalize it, okay? If we check for 7, p equals 7. Okay, let's check p7. Again, first number a1 is 2, a2 is 2 squared minus 1, 3. a3 is 3 cubed minus 1, 26. 26 mod 7, we can say is negative 2. a4, negative 2 to the 4, 16 minus 1, 15, which is 1. a5 is what? 1 squared minus 1, 0. a6 is what? 0 squared minus 1, negative 1. a7 is what? Negative 1 to the 7 minus 1, negative 2. a8 is what? Negative 2 to the power of 8 minus 1. And if you want to calculate negative 2 here, we should use little Fermat's theorem. That's the reason that we are checking more small example. We can find more ideas that are useful. Idea 3. Let me write it here. Little Fermat's theorem. It is what? We can say a to the p is congruent to a mod p. P is prime. Or one explanation is this, or you can say GCD of a and p is 1. If GCD of a and p is 1, then a to the p minus 1 is 1 mod p. And you can prove both these explanations are equivalent. And if you want to prove this, you can I can explain for you the proof, but you don't need to prove it for the exam. But if you wanted to know the proof, you can send message to my WhatsApp number in the description. You should consider A2, A3, A to P minus 1A and prove that it will be mod, it should be 1 to P minus 1 mod P in some order. And then you should consider the product and cancel P minus 1 factorial from both sides. But if you want to know the rigorous proof, as I said, you can send message to my WhatsApp number. Negative 2 to the power of 8. I want to see this one mod, then minus 1. This one mod, 7 is what? So it's 2 to the 8 because 8 is even. And we know 2 to the 7 is 2 because of this part. Or you can say 2 to the 6 is 1. It is 2 squared, okay? It's 4. 4 minus 1 is 3. A9 is what? So if you check negative 2, 1, A9. Okay, next one is what? 3. 3 to the 9 minus 1. 3 to the 9 is what? We know that 3 to the 6 is 1 mod 7 by Little Fermat's theorem, so it will be 3 cubed. And 3 cubed is 27. 27 is negative 1 mod 7, so it's negative 2. So let's see, do we have this period? 3, negative 2, and so on. So let's see. Here it is, we should raise previous one to the power of 2. We should raise previous one to the power of 3, to the power of 4, to the power of 5, the power of 6. And we can say it is to the power of 7. We can say to the power of 1. A to the 7 is A. This one again is to the power of 2, to the power of 3. And as you can see, this negative 2 is to the power of 3. So next one will be same. So if we consider this period, but as you can see, it starts from 2. Here it starts from negative 2. So let's write and see. Next one, beginning number would be what? Let me check this. Okay, a to the 10 is what? We should raise to the power of 4, it's 1. A to the 11, it will be 0 to the power of 5. A to the 12, it's to the power of 6. And it's negative 1. And again, we have same thing. Then a to the 13 will be to the power of 1. It's negative 2. So as you can see here, these numbers are 1. A10, A4, the period is 6. You can say A, 6K plus 4 are 1 mod 7, okay? Again, I don't want to write K, for example, W. So if I consider X6W plus 5, I want to find V7 of this, okay? So V5 or V7 of this is what? V7 of X A6W plus 4, the 6W plus 5 minus 1. And because it is 1, we can apply LT. It will be V5 of V6W plus 4 minus 1 plus V5 of 6W plus 5. So I want to do what? 6W plus 5. And this one we know is at least 1 because it is 0. And we want that this one be multiple of 7. Sorry, why I wrote 5? I should write 7. B7, it is at least 1. Because you can prove by induction because we have these two things. Again, this part will be repeated. Okay. And it is at least 1. So this one should be at least what? At least k minus 1. Then some of them will be at least k. And then this one will be multiple of 7 to the k. 6w plus 1. If it is 0 mod 7 to the k minus 1, I should find at least 1w that it's multiple of 7 to the k minus 1. It's easy because you say, okay, 6, it's negative 5 mod 7 to the k minus 1. And 6 has a, we can say, multiplicative inverse mod 7 to the k because GCD of 6 and 7 to the k minus 1 is 1. Then there exists a number, we can call it 6 inverse. It is a number, an integer, not 1 over 6. But in modular arithmetic, we can write like this. Or if it is not good for you, you can say, okay, multiplicative inverse of this, suppose it's b. 6b is 1. Mod 7 to the k minus 1. So we can multiply both sides by b, so w is congruent to negative mod 5b, mod 7 to the k minus 1. So you can add 7 to the k minus 1 to reach a positive integer. So we have infinitely many w that satisfy this. And for this multiplicative inverse, I can prove it for you. Let me tell you idea 2, idea 3, idea 4. Suppose GCD of a and b is 1, then there exists x such that ax is 1 mod b. Okay, so x is multiplicative inverse of a mod b. Okay, the reason is what you should consider a to b minus 1a. And we want to prove that one of them is 1 mod b, and then the problem will be proved. So first I want to prove that they are different. They are different mod b, 1, 2 to b minus 1. Okay, mod b. How we can prove this? First I want to prove that they are different mod b. If IA is congruent to JA mod b, we have a rule in modular arithmetic if AM, or we can say AB is congruent to AC mod M, then it is equivalent. You can divide both sides by A, but you should pay attention that you should write M over GCD of M and A. It is so much important. And we can prove it. If you want to know the proof, again, you can send message to my WhatsApp number. This one, then by this approach, you can say, okay, we can divide both sides by A, but GCD of B and A is 1, so mod B. But we know these coefficients are 1 to B minus 1, so they cannot be congruent mod B. So they are different, and none of them is 0 mod B, because if it is 0 mod B, we know A and B are relatively prime, and 1 to B minus 1 are non-multiple of B. So we can conclude what? They are different mod B and not 0, so they should be 1 to B minus 1 in some order, because number of them equals B minus 1. So one of them is equal to 1, that's multiplicative inverse. For example, K times A, T times A is 1, and exactly that is multiplicative inverse that we want. Proof of Little-Fermat's theorem is similar. Now that we prove this, so we have multiplicative inverse, we can multiply, and then we have a good W. So we proved for 7, and we understood, okay, we should find this period, and we should pay attention to Little-Fermat's theorem. Now let's generalize it. You know A1 is 2, A2 is 3, A we should raise to the power of 1 here, we can consider power of 2, power of 3. And this one is what? 26, and so on. Now we know until AP minus 1, we should raise to the P minus 1. Then for AP, we can consider raise to the 1. So we have this length. Then again for until A2P minus 2, we should write to the power of P minus 1, like 7 that we said until 12. Okay. Length of this period is P minus 1. Okay, so if we find equal, for example, A1 equals AP, then these two things will be similar. Again, for next one, just consider A2P minus 1, should raise to the power of 1 to A3P minus 3. It is P minus 1, and so on. Like a small examples that we checked, we want to find something 1 or negative 1. Let's see how we can find that. If we use Little-Fermat's theorem, we can say, for example, for AP, or let me tell you, AP minus 1. AP minus 1 is what? Is equal to AP minus 2 to the power of P minus 1 minus 1. So we have two cases. Case 1. If AP minus 2 is 0 mod P, then what happens? AP minus 1 is what mod P? Calculate this. 0 minus 1, negative 1 mod P. Case 2. If AP minus 2 is not 0 mod P, means non-multiple of P, so relatively prime to P. So AP minus 1 would be what? This one would be 1, 1 minus 1, 0. Okay. And as you can see for these cases also we have same thing. Okay, because when you raise to the power of P minus 1, we said it's equivalent to P minus 1. So the previous one is important. If it is 0, then next one is negative 1. So let's consider cases. Let me move it down. And okay. If previous one is 0, this one would be what? Negative 1. Negative 1 to the 1 minus 1 is minus 2. And minus 2 squared minus 1, 3. Or if it is not 0, then this one would be 1. And I'm sorry. If it is not 0, this one would be 0. Then 0 to the 1 minus 1 is negative 1. Negative 1 squared. 1 minus 1, 0. Now we can see the first one from second group or second box. Can be start with negative 2 or negative 1. Okay. Now, if again next one, for example, is negative 2, the next one obviously will be negative 2 like this. So, again, we can write for this part 0, negative 1, negative 2, 3, or 0, negative 1, and 0. So we can go to this part, or this part, or this part, or this. We have these four cases, okay? So let's check them. Okay. If we check them, we can see that this part is what? We can go from negative 2 to negative 2, or from negative 1, for example, suppose we are focusing on only these parts. Why here I said, oh, sorry. Here I should correct this. This part, negative 2, 3, negative 1, and 0. Okay, this, or this one, or this one, or this. If we go from this part to this part, we can show it like this, negative 2 to negative 2. If from this part we go to this part, negative 1 to negative 1. If we go from this part, negative 1, to, for example, this part, that is 2. After that is important. If from negative 1 we go to negative 2, and from negative 2 again to negative 2, it will be similar to this. Or if we go from, for example, negative 2 to negative 1, and then here, it will be here. Because after that, next step, we go to negative 1 and negative 1 and negative 1, and so on. Or maybe we go from negative 1 to negative 2, negative 2 to negative 1. So we have these three cases, and we should check them. Okay, so for this one, negative 2 goes to negative 2, negative 1. Let me write this 0 below this one. It's for A2P minus 2. And so, like previous cases, when we found, for example, some 0, we should consider, okay, A5 in terms of A4. For example, we found that x6w plus 4 is 1. And then for next one, we use this one. So previous one is important. So let's calculate for these zeros. Let's calculate before that is what? Okay. We know something to the power of p minus 2. So we know it is AP minus 2, for example. AP minus 2 is what? Is 0. AP minus 2, or if we want to write general form, it is 2p minus 3 raised to p minus 2. So it will be what's a p minus 1 times z plus p minus 2, okay? It is equal to what? It is equal to a times p minus 1 times z plus p minus 3 to the power of p minus 1 z plus p minus 2 minus 1. If we consider this part mod p, we can say this number mod p minus 1 is what? Is 1 if it is not 0. And we know it is not 0. Because if it is 0, then 0 minus 1 is negative 1. And this p minus 2 should be for this purpose. Okay. We are considering which numbers? We want to consider these numbers. Okay. So as you can see, for example, when it is 2 times p minus 1 plus z is 1. Z is 1, p minus 1 plus p minus 2, 2p minus 3. If z is 0, it will be this. Okay. So p minus 1 times z plus p minus 2 minus 1. So it is not 0 because if it is 0, then 0 minus 1, negative 1. So next one, this one will be negative 1, not 0. So it is not 0. So we can use Little Fermat's theorem, and the power of this one is 1. So it is a p minus 1 z plus p minus 3, the power of p minus 2 minus 1. And we know this part is what? This part is 0. Okay. So we can say a to the power of p minus z plus p minus 3 to the power of p minus 2 is 1 mod p. And we can say what? We can multiply by a p minus 1 a this sub. And then this side will be a to this one to the p minus 1 by Little Fermat's theorem is 1. So a times p minus 1 z plus p minus 3. So we can conclude previous number is 1. Okay. So when we have 0, previous number is 1. When we have 0, previous number is 1. Okay. Now we can use LTE, lifting the exponent. How? We can say what? We can say, okay, a to the p minus 1. We want to find what? VP of this. Okay, VP of a, this one, p minus 1 z plus p minus 2 is equal to what? Is VP of a p minus 1 z plus p minus 3 to the power of p minus 1 z plus p minus 2, by definition assumption of the problem, minus 1. And because we know it is 1 mod p, so this one minus this one is multiple of p, so assumptions of conditions of LTE will be satisfied. So we can write it as VP of a p minus 1 z plus p minus 3 minus 1. This one is at least 1 because we proved this one is 1 mod p, plus VP of p minus 1 z plus p minus 2. Okay, so if we prove that this one can be multiple of p to the k minus 1, then for this case, problem will be solved. How we can prove this part? We should say, okay, p minus 1 z plus p minus 2 should be 0 mod p to the k minus 1, right? So we can say p minus 1 times z congruent to 2 minus p mod p to the k minus 1. So because p minus 1 GCD of this and this, GCD of these two numbers are 1, we can easily prove. So we can multiply by multiplicative inverse of p minus 1. We prove there exist, okay? By idea 4. Let me tell you why the GCDs are, let me cut it. Let me tell you why the GCD is 1, because if you consider GCD of p minus 1 and p to the k minus 1 d, then we know d divides p minus 1, d divides p to the k minus 1. Okay, and from here we can say p is 1 mod d, and from here p to the k minus 1 is 0 mod d. So from here you can raise both sides to the power of k minus 1, so p to the k minus 1 is 1 mod d. And by considering these two things, we can say 1 is 0 mod. Okay, so d divides 1, the difference, and d, because by definition of GCD that is positive, d is. There are lots of other ways. You can say, okay, if GCD, if consider GCD of these two things, because d is a divisor of this, is p to the power of something, and p to the power of something is not divisor of this. There are lots of ways to prove this. Okay, so because we can multiply by multiplicative inverse, so we can say z is equal to p minus 1 inverse. We can write it like this. And as I said, this is integer, not 1 over this. We consider mod p to the k minus 1. Okay, z is this one. And then this one will be satisfied, so this one is at least k. And you can add p to the k minus 1 to reach a positive number if it is negative. There are infinitely many with z. So 1, 2. Now let's check case 2. Okay, if negative 1 goes to negative 1. Okay, for this negative 1 goes to negative 1, we should erase this part. Let me erase this part. Negative 1 goes to negative 1. So let's move it here. Okay. And then we can say what? Negative 1 goes to negative 1. Next one, 0. And we can say we wanted negative 1 or 1. And this is 0. So this is what AP plus. This one is 0. A2P is also 0. So these numbers are what? Because the length is P minus 1, we can say A P minus 1 times, for example, T plus what? For example, P minus 1 plus 2. Okay? Plus 1, sorry. If T is 1, it is P. If T is 2, it is 2P minus 2 plus 1. It will be 2P minus 1. They are negative 1. Okay? Mod. And because from negative 1 we reach negative 1, again we reach negative 1, and so on. Now, if we consider a P minus 1, now we want to consider. And this number, next one, reaches to the power of 2. Equivalent to power of 2. So let's consider Vp of a P minus 1 T plus 2. Okay, so these numbers. It is equal to Vp of AP minus 1 T plus 1 to the power of P minus 1 T plus 2 minus 1. Okay? And then we can say what? We can say it is even and it is negative 1. So we should write like a small examples that we check. AP minus 1 T plus 1 squared of this over 2. P minus 1 T plus 2 over 2. P minus 1 is even, 2 is even, so sum of them is even, minus 1. Now, conditions of LT are satisfied because this is negative 1. Mod P, this squared is 1. So this minus 1 is multiple of P. So we can apply LT. It will be A P minus 1 T. Let me write. P minus 1 T plus 1 whole squared. And minus 1 plus VP of this one is P minus 1 T plus 2 over 2. Okay, so we know this one is at least 1. We should prove why this one can be at least K minus 1. So we should find a good T that, because 2 has no effect on P. So if it is multiple of P to the K minus 1, this one also is multiple of P to the K minus 1. So P minus 1 T plus 2 should be 0 mod P to the K minus 1. Again, like previous one, you can take 2 to right hand side and multiply by this inverse. So T is congruent to negative 2 times P minus 1 inverse mod P to the K minus 1. Okay, so we proved also this case. Okay, for this part, negative 1 goes to 2 without loss of generality. Suppose, for example, here we have negative 1. Sorry. For this one, negative 1. And this part, negative 1 goes to negative 2. So this length. And this part, 3P minus 2 to this one. Okay. Negative 1 0, 0. Then it goes to what? To negative 2. Before negative 2 is negative 1. And negative 2 goes to negative 1. Again, 0, 0. Okay. And so on. And again, negative 1 goes to negative 2. Like this, negative 2 goes to negative 1. So we can say our period is this part. Okay. So let me erase this part. Okay, let me raise the power of what? Here, raise the power of 1, raise the power of 2, raise the power of p minus 1, again, raise the power of 1, raise the power of 2, raise the power of p minus 1, raise the power of 1, raise the power of p minus 1, raise the power of 1, raise the power of p minus 1. Okay, now we can consider what? Let me erase this part. Okay. The length of this period is 2p minus 2. Okay, and it's not important. It starts from negative 1, negative 2 here, or negative 2, negative 1. Now, what number is good here? We want to find the one that we had. We said it is what? Negative 1, 0. Before negative 2, negative 1, 0, 1. Negative 2, negative 1, 0, 1. 0 and 1. We have this. Okay? So this number is what? A 2p minus 2, 2p minus 3, 2p minus 4. Okay, so 0, 1. It's a 2p minus 4. What's the next number that has this property? Next one is a. You should add 2p minus 2 because p plus 2p minus 2 is this one. 2p minus 2. So we can write 2p minus 2. For example, I plus 2p minus 4. Okay. Now we should consider next number that is 0 and apply LTE. We know. So if we consider VP of A times 2p A sub 2p minus 2i plus 2p minus 4 plus 1 2p minus 3, this is congruent to what? VP of A 2p minus 2i plus 2p minus 4 to the power of 2p minus 2 by assumption of the problem plus 2p minus 3 minus 1. Now we can apply LTE because this this is 1 mod p. By induction you can prove, and we proved this in previous part. Then because it is 1, this minus 1 is divisible by p, and this one are not multiple of p. So we can write VP of A 2p minus 2i plus 2p minus 4 plus VP of this, the power 2p minus 2i plus 2p minus 3. This one is at least 1. We should see for which I it is at least k minus 1. Then this part will be at least k. And the problem will be solved completely. So 2p minus 2i plus 2p minus 3 should be 0 mod p. Okay? Mod p to the k minus 1. So we can say 2p minus 2i should be congruent to 3 minus 2p mod p to the k minus 1. If you take this to right hand side. And we should multiply by this inverse because this and p are relatively prime because p is odd and p and 2 are relatively prime. So p and p minus 1 also relatively prime because it is 2 times p minus 1. Okay. So we can multiply by this inverse. So I is congruent to 3 minus 2p times 2p minus 2 inverse mod p to the k minus 1. So if it is negative, you can add p to the k minus 1 as much as you want, and you can find infinitely many good i's. So in all cases, we proved this problem. Let me tell you some homeworks. Okay, try this problem as homework 1, AIME 1 2020. You can solve it with similar idea. If you want to solve more problems from this idea, as I said before, or wanted to learn more background ideas, how to approach difficult problems in IMO, JMO, AMO, feel free to send message to my WhatsApp number in the description.